Hey everyone, and welcome to another episode of C++ Data Structures. My name is Nick, and today we're going to continue our look at basic sorting algorithms, now looking at insertion sort. So previously we had looked at selection sort, where we built up a partially sorted list, we built up a sorted sublist starting from the smallest elements, and gradually expanding that sorted sublist until we finally sorted the entire list. And then we looked at bubble sort, where the larger values trickled up all the way to the top, and we built a sorted sublist starting from the larger elements, working our way down to the smaller elements. So in this example, we're going to look at insertion sort, which does things a little differently. And the reason why is because we're not using any swap anymore. We're using insertion. So what happens is we will have a sorted sublist at the very far left, similar to selection sort, but this time what we're going to do is we're going to take the element that's immediately to the right of the of our sorted sublist. So at the very beginning, our sorted sublist will just be whatever's at index 0, and then our next item will be whatever's at index 1. And what we'll do is we will insert whatever's at index 1 into its correct position between indices 0 and 1. And then at that point, that sublist right there is sorted with respect to those two elements. Now, it's not necessarily sorted with respect to the rest of the list, but compared to those two elements, it is in the correct order. And what will happen then is it will gradually move over and over and over. So then we'll look at, instead of index 1, we'll look at index 2, and we'll insert index 2 into the correct spot. And occasionally we'll have to shift all of the elements over in order to make space for the insertion. We'll have to do that a lot of times. So let's actually look how we implement this so it'll be more clear. So we're going to look at insertion sort.cpp. And so here we have our function for insertion sort. So the first thing we need to do is we need to have this temp variable. And the reason why is because, like I said, we have a limited amount of space that we're working with. You know, our array is only so big. So if we want to, kind of make space or shift over elements, that means we're going to have to delete an element if we want to shift everything over one. And we only ever need to make space for one element at a time because we're only inserting one thing at a time. So what we'll do is we'll start at index I equals 1 because, like I said, our sorted sublist will start at index 0. So if 0 is the only thing in the sublist, then it's implicitly sorted. So the first thing we do is we will save whatever's at position I, so the element that we're inserting. And what we'll do is we will check to see how much we have to shift over by. So in this case, it will be I minus 1. So in this case, it will be 0. And the reason why that is because there's nothing in the list right now, right? So, or rather, this j value will be 0. And so the way we shift over is using a while loop. And while we check to see if j is greater than or equal to 0. So even if j is equal to 0, that just means we have the potential for needing to, say, move the 0th element still over to the right one so we can put whatever's in index 1 in index 0. So that's why we have to save it as a temp right here. So we check to see if j is greater than or equal to 0. Because, like I said, we're working our way down the list. So the element we're inserting is on the right side of this partially sorted sublist. And what we'll do is we will move down the list and we will gradually shift these elements over to make space. And eventually we'll find the gap that it fits in and we'll insert it into that gap. And so to shift over, it's very simple. We will just put whatever's in array of j into whatever's in array of j plus 1. And we don't need to worry about overwriting because we saved what originally was in the ith element here. So in that, into the first iteration of this while loop, we'll immediately overwrite whatever was in this location of location I, because j plus 1 will equal I, right? So everything will shift over. And then of course we have to decrement, right? And the reason why we decrement is because we're moving over to the left inside of the list. So instead of moving to the right, all of our previous ones, we had gone over and over and over, and we'd been moving towards the right of the list. This time, we're starting at a position not necessarily all the way at the end of the list, but the end of our sorted sublist. So it starts out at index 1 and moves all the way up to index n minus 1. Okay, so then at the very end, when either when we get to the very beginning of the list, or the point where we get to if array of j is less than or equal to temp, that means we found a location where this element fits in. So what we'll do is we can simply just insert it by putting whatever's at j plus 1 into temp. Okay, and then we'll go ahead and just print it out. So this will become more clear when we look at a visual example. So let's look at our main function. So we're just going to be looking at a 7-element array, and we'll go ahead and just fill it with some random numbers using rand, and then we'll just call insertion sort. So let's go ahead and compile this, and let's run it. All right, so let's go to the very top. So where do we start out? So we start out, like I said, from index 1, so I is equal to 1. So 83 is implicitly sorted. So that's this sorted sublist here. That, remember, it's sorted with respect to itself here, but not in respect to the remaining elements over here inside of the list. So what we end up doing is we check to see if we go ahead and start moving elements over until we find a spot where this element is less than or equal to this element. So in this case, we're inserting whatever's at index 1, and we find out we don't need to move 83 over to the right because it's less than 86, so it just stays in place. And now we move over to the right one, so that outer loop ticks to plus 1. So in this case, we look at index I is equal to 2, so now we're inserting 77 into this sublist right here. Now 77 is not in the right spot, so it doesn't belong in index 2. It belongs at the very 0 position of the list. So what happens is in that while loop, we walk over, we save 77 as a temporary variable. That way we can move 86 into 77's spot, 83 into 86's spot, and then we finally insert 77 into the beginning of the list. And then we have this sorted sublist here. So 77, 83, 86, all ascending, so it's in the right order. Okay, and then we check whatever's at index 3 now. And so we do the same process. So index 15, we see where it needs to get sorted. So 86 moves over, 83 moves over, 77 moves over, and then 15 gets inserted at the 0th position in the list. Then we get over here to 93. So with 93, we compare it to all the previous elements. And so we already find that 93 is not less than 86. So it just stays in place. That while loop never gets executed. So it stays. Okay, and then finally we get here, the last two iterations, or last couple iterations. Yeah, so what we do is we look at 35. So 35, we compare it to 93. Turns out 35 is, of course, less than 93, so we move 93 over 1. We move 86 over 1. We move this 83 over 1. We move 77 over 1. And we have this gap right here because we move 77 over, but we find that we're not smaller than 15, so we just insert it right here where 77 used to be, and 77 and all of these others push over. Okay, and then we get this sorted sublist. So everything up to this point is now sorted. So this is in the correct order. So then we're on our last iteration. So now we need to check to see where the last element fits into this list. So unlike the other methods where we got the last iteration for free, in this method we have to insert the last element in the list because, like I said, we're guaranteed that everything in this sublist will be sorted with respect to each other, but not that it's sorted with respect to other elements in the list that haven't been inserted yet. So we look at 86, we move it over past, so 93 moves up, And then we find that 86 and 86 are the same value, so we don't need to move over anymore. So we just insert 86 right there. We don't need to move over anymore because even if they're the same value, it doesn't matter if we put it on the left or the right. So it's better to just put it on the right because then we don't have to do another shift. Okay, so that's going to be insertion sort. Now you can see directly, if you remember the earlier data structures videos that we did, there's a data structure that this maps really well to, and we'll look at implementing using that data structure. And that's a linked list. And so you may be wondering, well, why does this type of sorting map well to a linked list? Well, think of it in terms of this operation of moving all the items over. Now we had to do this while loop to move all the items over because we had an array itself doesn't maintain any kind of order. It just holds elements. Now think about this if each of these pieces of data right here was instead a node. Now in the case there, all we would need to have is a method for inserting a node. So if we inserted a node into, say, position 1 here, all I would need to do is make 15 point to 35, and then make 35 point to 77, right? And then when I take this out, I need to make sure 93 points to 86. But these interior nodes, they're absolutely fine the way they are. I don't need to worry about moving them over at all. Their pointers still point to the correct thing. So we'll look at how we can implement this with a singly linked list in a later video. But that's going to do it for this time. As always, you can go to github.com/coffeebeforearch to look at all the other videos in this series, as well as any of the other series like the Python, the multiprocessor programming in C++, the CUDA crash course that we look at programming on GPUs. So this was C++ data structures. My contact information here is if you have an example that maybe you'd like. In another series, we'll be doing some study on algorithmic complexity, and we'll be looking at all of these different sorting algorithms and even plotting them out and seeing, at different sized arrays, how do they perform, and really mapping back their computational complexity to, figures that we can look at and visualize. And of course, here's all links to all the videos and the files used in these videos. So we looked at insertion sort today. So feel free to download this, play around with it, and have some fun with it. So as always, I'm Nick from Coffee Before Arch, and I hope you have a nice day.